Okay, we are now at the point in our study of bonding and understanding molecules to be able to put together the ideas of the molecular shape and electronegativity. And when we do that, we get what is called polarity in molecules. Polarity in molecules helps define their physical and chemical properties, and so it's an important one for chemists to know. What we're going to do today is we're going to go to a simulation. And so if you look up here, I've plugged in on Google PhET simulations, and that will take me to the University of Colorado site. And we are going to be watching molecular polarity. That is the specific one. So if you want to go directly there, you can copy this URL, phet.colorado.edu /en/simulation/molecule polarity, and I would like you to take the opportunity to do this. You will need to download and run this. It requires that you have Java running, which is an operating program that's made for both Macs and PCs as well as Linux, if I'm not mistaken. So when we click on this, it'll ask us to download it and play with it. I have done this already. So make sure that you're up and running, and you will eventually get to this screen where we can talk about polarity as it ties in with electronegativity. So on this screen, I've got two atoms. That's what the A and B are representing. And this turns to a circle so that I have the ability to rotate the molecule. And then atom A and atom B, I can define what their electronegativity is. So let me just play a little bit with this. Currently I have bond dipole clicked on, as well as partial charge. Electron density is clicked on, but I've turned off the electric field. So when I take electronegativity and bump it up, I get this growing black little arrow, which tells me that the electrons in the bond between these two atoms is tending toward B and away from A. Now the little plus sign that you see here tells me that this side of the molecule is going to be partially positive, and the right-hand side will be partially negative. And the more electronegative B gets, the bigger the arrow gets, the larger the partial negative and partial positive charges grow. Now, let's apply an electric field. And when I apply the electric field, if I rotate the molecule this way, it bumps to the right because the partial negative charge is attracted to the positively charged plate here. It would not move quite as quickly if it has very, very low electronegativity because the attraction isn't quite as great, and that's indicated by the speed of the rotation. So if they have equal electronegativity, and I'll try to put them both at half, then if I rotate the molecule, it indicates that neither atom is favored by that electric field. Let me bump up the electronegativity of B and bump down the electronegativity of A and point out that this side of the molecule is a little bit darker. That's because I have electron density clicked. I'm going to change that to electrostatic potential, and the red side is the partially negative, and we can prove that by fading this down. And now basically they both have the same electronegativity and there is no potential left or right. Rotate the molecule, we'll see that the electric field does not affect the molecule. So that is how two atoms work, and we can play with these controls, and I invite you to do that on your own. I want to move along to a 3-atom setup, and once again I have molecular dipole clicked, and I'm going to click on the electric field so that it's working. So currently, if I make B more electronegative, it is very much attracted to the positively charged plate. And if I take, oops, I don't want to do that, I'm sorry. If I rotate the molecule, B is going to end up pointing back there. Okay? So 3 atoms creates a slightly different scenario. If I bump up the electronegativity on C, boom, it's attracted to the positive plate. But what if I also do that on A? Look where that arrow is going. That arrow is going so that A and C, which are both electronegative, are attracted toward the positively charged plate. Let me click on bond dipoles. Can you understand the relationship between these lines, the black lines, and the bond dipole? This B to C arrow is forcing the electrons towards C, and the B to A arrow is showing that the electrons are going toward A. So here the electrons are going toward C, the electrons are going toward A. The result of both of those forces, in other words, if I were to add the up characteristic and the over characteristic to the down and over characteristic, they would end up with a net electrostatic force going toward the positive plate. So the resultant of these two vectors is going to be an attraction toward the positive plate. Let's change things a little bit. I'm going to move the atom C to be directly in line with A. And notice as I move C closer and closer, what happens to the yellow arrow, the resultant arrow? The molecule's shape determines its polarity. Now I have just canceled out any polarity in this molecule. So if I don't want to rotate that at all. If I rotate the molecule, it doesn't matter which side is pointing toward the electric field, the forces cancel out. So when we talk about the shape of an atom, how we orient that molecule will change the direction of the electrostatic field so that the bond forces an attraction toward the positive field. It creates a force, and we can increase the strength of the force by decreasing the bond angle. So now this and that are adding up to equal a net negative attraction toward the positive. Let's see how this plays out in some real molecules. Once again, I invite you to play with this model so that you get an understanding. Let me do one thing before we leave. We're going to put everything in line and set the dipoles all to 0 so that there is no net electronegativity difference. But now I'm going to make A slightly negative, but I'm going to make C very much negative. So you can see that a small attraction to the left for the electrons is outweighed by a net attraction to the right towards C. And that's because there's a difference. What would happen if A was not electronegative at all, but B was a little bit? Then I still get that net attraction toward the right-hand side. So I just recommend you play with those. Okay, so this is the molecule hydrogen, H2. It is using 2 hydrogen atoms, and they just call it hydrogen 1 and hydrogen 2 so that we can show the difference between it. And I want to show you on the surface the electrostatic potential. So they throw around these spheres to indicate whether it is positively or negatively charged. And since we're right here in the middle, there is no net positive or negative. Although these are electrons, they are equally distributed all over. So this is what is called a nonpolar molecule. There's neither an attraction to the right or to the left-hand side. Okay? And then we're going to go to nitrogen. Nitrogen, if you recall, has a triple bond in between it, and it has a very similar electrostatic potential as hydrogen did. The triple bond doesn't seem to make any difference, even though there are loads of electrons right in that area. Let's look at bond dipoles, molecule dipoles. We don't see any change at all from what you would see in hydrogen, except there are actually more electrons there. But let's go to hydrogen fluoride. And let me take off all of the pretty things. Hydrogen and fluorine shows that the right-hand side of the molecule is slightly negative. So I'm going to throw on my partial charges here, and you can see the difference in electronegativity results in hydrogen being partially positive and fluorine being partially negative. This whole red cloud indicates the partial negative, and the blue cloud the partial positive. So if we were to look at the electronegativities of the atoms, you would see that fluorine is 4 and hydrogen is 2.1. Fluorine is much more electronegative. What is the net dipole of this atom? It is definitely going toward the right, and that's obvious from our picture. So the little polarity arrow that we would draw indicates an attraction to the fluorine for the electrons in that bond. The result of that attraction is the molecule has a dipole, or it is a polar molecule. Well, let's look at water. Water has 2 hydrogens, one hydrogen to the left and one to the right, and then the oxygen. And the oxygen is very electronegative compared to hydrogen. And as a result of the shape of the molecule, if you remember, there's 2 lone pairs of electrons which would roughly be in this area. But it's not the lone pairs of electrons that make water electronegative, or the oxygen electronegative. It's the result of oxygen's ability to attract electrons in these 2 bonds. So this end of the molecule tends to be very negatively charged. A partial negative charge, not a total negative. As you can see, it's 0.75. And this side of the molecule by the hydrogens tends to be electropositive. So the molecular dipole is going up. Let's look at the individual bond dipoles. They're both being attracted toward the oxygen. So what's the net effect of that? Is that the electrons are much more attracted to this side of the atom than they are to the other. So let's click off on these again and look at another one. Ammonia. Ammonia, and we can move the molecules around here a little bit to get a better view. Ammonia is a trigonal pyramid. There's a lone pair of electrons here, and then there are 3 hydrogen atoms at the base. So these hydrogens at the base end up being partially positively charged. That's why they're blue, and the nitrogen is very electronegative compared to hydrogen. So the electrons in the bonds are attracted toward this end of the molecule. This makes ammonia, NH3, a polar molecule. Let's look at another molecule that we have actually drawn, and that's going to be methane. Methane is a tetrahedral shape, and the tetrahedral shape of methane lends itself to there being essentially no polarity to the molecule. You can see a very light blue, very light red in these various regions around the molecule. But the result of all the bond dipoles, in other words, the hydrogen is attracted to the carbon, but their bond angles as such that they cancel out. So when I click on molecular dipole, there is no molecular dipole to be found anywhere in this atom whatsoever. Okay? Let me click off on these again, and we'll start with a new molecule. This time we are going to look at the same molecule, but this time there is a fluorine that has replaced one of the oxygens, or of the hydrogens in methane. So fluoromethane is now an electronegative because this region up here where the fluorine is attracting the electrons in the bond, and that makes that end of the molecule more electronegative. Let's look at the electronegativities of the atoms. Once again, hydrogen is not as attracted or doesn't attract electrons as well as carbon does, and fluorine does it much better than both. So this part of the molecule is extremely electronegative, and this leads to a polar molecule. Let's check out the individual bond dipoles, and you can see, there we go, if we get the right angle on this, you can see the bond dipoles between the hydrogen to the carbon. And where is that bond dipole to the fluorine? It's going to be this right here. And as a result of that, the molecule has a net polarity. We say it has a dipole going to the red region up around the fluorine. All right, and I was hoping to do carbon dioxide as an example of a molecule which has polar bonds. So carbon is here in the middle. There's a double bond to the oxygen on the left and a double bond to the oxygen on the right. A small difference in polarity, but clearly this end of the molecule, where the oxygens are, is more electronegative than the middle. And in fact, there is a dipole. The carbon to oxygen bond is a bond that is polar, but they're oriented in space so that they end up canceling each other out. So when I click on molecular dipole, we should see something if there were a bond dipole, but indeed there's not, and so we do not see anything end up on the diagram here indicating that it is a polar molecule. Let's take one look at another 3-atom molecule. We looked at water already, which was polar. We looked at carbon dioxide, which was nonpolar, and water has a bent shape, 109.5 degree angle, actually 104.5. Carbon dioxide is linear, and it has a 180 degree angle. And now let's take a look at ozone. And let's pull off the polarity arrows. And looking at ozone, we can see that it also has a bent shape. Let's take a look back at our records to see how we drew the Lewis dot structure for this molecule. Here is ozone. It has a single bond and a double bond, and there is a lone pair of electrons on the oxygen. So the result of the analysis of this is that we have 3 electron regions around the oxygen, central atom, and there are 2 bonding regions and 1 non-bonding. Let's look at our analysis of what that means, is that there are 3 electron regions. That means there is 1 lone pair, 2 bonding regions, and that leads to a bent or V-shaped molecule with a bond angle of approximately 120. This is the bent or V-shaped with a 120 degree bond angle. So going back to our diagram, the angle here is 120 degrees. And you can see that in between these 3 atoms, there is individual bond dipoles, and there is a little tiny bit of a molecular dipole due to the shape of the molecule. If this molecule was linear, we would not expect to see that, but because of the shape of it, we do see a little bit of polarity to the molecule. So I invite you to check out some of the other features of this website. It'll give you a great opportunity to explore polarity and get a better understanding of how that applies to molecules. Thanks, and look forward to seeing you in class.